Okay, so this one, the thing that happened with this one for us, for lots of us, is that we were distracted by the fact that this was a proof by induction that you have the skills to do without proof by induction. But that doesn't matter, because there's lots of things you can do without proof by induction. But if the question says prove by induction, you have to do what the question says. Okay, so the question didn't say prove, it said prove by induction. So the first thing to not do is you don't expand this left-hand side. You don't write it as 3 sigma r squared plus sigma r. You don't turn that into the formulae, because what we ended up happening in quite a few cases was we had people who were what does that give us? I'm going to delete this in a moment because it's obviously it's not what we want to do. But that's the right formula, isn't it? Plus half n plus 1. Right. That's right, isn't it? That's what you get. Now, that does equal that. Obviously, of course it does, because that's what you get when you expand a bracket. But the thing that you've been asked to prove by induction is not that that equals that. The thing that you've been asked to prove by induction is that the sum of that series equals that. And there's a difference. Okay? So, as soon as you started using the standard series, you'd kind of destroyed your chance of getting any of the proof by induction marks. And you proved it, and I think almost everybody proved that statement was correct. But not many people proved it by induction, and the question was about induction, not the standard series. Okay, so what a few of you did really well was a really good proof by induction that this is the same as that. But getting from there to there is a really trivial thing. It's just factorising this expression, and that's not the thing that we want to prove. So that's another thing that we've learnt from doing this, although I think we knew it already, but it's another thing that we've learnt, that a question about proof by induction means that you have to do it proof by induction right from the start. You can't use any sums of series, any standard results to do it first. So, actually, that means what we're doing is we're starting and we're saying if n equals 1, let's check that both sides are the same. We need to show enough working out to show that we know what we're doing with this. So we're checking the sum as r goes from 1 to 1 of r 3r plus 1. Well, that would be 1 times 3 plus 1. So it's 1 times 4. So that would be 4. And the right-hand side is 1 times 1 plus 1 squared, which is 1 times 2 squared, which is also 4. So that's what we wanted it to be. So we've verified it, proved it for n equals 1. Now we state our assumption. So we're going to assume that this is true for n equals k. That means that the sum as r goes from 1 to k of r 3r plus 1 is k plus 1 squared. There's our assumption clearly stated. Now we need to prove that it's true for n equals k plus 1. And this is this thing where over here, quietly, so that nobody notices, we're going to show what success would look like. What we're trying to prove is that the sum, oh that's an awful sigma, the sum as r goes from 1 to k plus 1 of r 3r plus 1, well, if we sub in k plus 1 into that, that would equal k plus 1 times k plus 2 squared. So that's where we're heading towards. That's what we'd like to achieve. So now we need to try and achieve it. So what is the sum? The sum as r goes from 1 to k plus 1 of r 3r plus 1 is equal to, well, adding up to k plus 1 is the same as adding up to k and then putting on the k plus 1th term at the end. So that is the sum as r goes from 1 to k of r 3r plus 1 plus the k plus 1th term. If you sub k plus 1 into this formula, you get k plus 1 times 3 lots of k plus 1 plus 1. Okay? We know that in this step of proof by induction we're supposed to be using our assumption. So here comes the assumption. We assumed that that was equal to k plus 1 squared. Adding on to that sum of the first k terms, we've got this expression here, which is k plus 1 times, what's in here, 3k plus 4. Is that right? Yes. So now we need to factorise this expression. Remember, in our mind we've got it heading towards that. So we know we need to factorise it because that's what we expect it to end up looking like. Looking at these two terms here, we have a common factor of k plus 1. So let's take out our factor of k plus 1. We'd have k plus 1 multiplied by k times k plus 1 in that first bit. It was k plus 1 squared. And here we'd have k plus 1 multiplied by 3k plus 4. So we're now factorising the big square bracket. The big square bracket says k squared plus k plus 3k plus 4. At which point we feel nice and warm and fuzzy about how everything's going, because look, that is k plus 2 squared. That's what we wanted. Ace. We got there. And all we have to do now is to round it all up with some kind of statement about something in the world. So if true for n equals k, then it is also true for n equals k plus 1. Hence, by induction, and here's where we write the result of the sum, as r goes from 1 to n of, what was it? r 3r plus 1 equals n plus 1 squared. Sorry, the board's just decided to stop. N plus 1, sorry, squared for all integer n greater than or equal to 1. And there we go. And that rounds it off. Okay. It was unfortunate because I felt that proof by induction was something that we were reasonably confident with, or at least we had a bit of a grasp of what was going on with it. And what happened was they threw at us one of the easiest proof by inductions that you could get, one of these series ones that, you know, sometimes the divisibility ones or the matrix ones can be a bit more confusing, but these ones, this should be the kind of the standard proof. And we panicked a little bit and turned it into a standard series proof and then missed the trick of doing induction with it. Okay, but there it was for 5 marks. It just followed through quite nicely. And that's proof by induction math.